Time dilation and length contraction. On September 26, 1905, Albert Einstein published his paper called On the Electrodynamics of Moving Bodies. This paper focused on the incompatibility of Newtonian equations with electromagnetism and the null result of the Michelson-Morley experiment. This led him to develop his special theory of relativity, which included relativity of simultaneity, relativistic Doppler effects, his famous equation E equals mc squared, and many more amazing concepts. His theory of relativity has modernized our understanding of physics, yet confuses physicists and students to this day. Two common concepts which tend to puzzle physics students are time dilation and length contraction. But before we can dive into an explanation of these, there are three things that are important to know about. First is Einstein's two postulates, which state the laws of physics are the same in all inertial frames of reference, and light propagates through empty space with a definite speed independent of the speed of the observer or source. In other words, you cannot tell if you are moving or still if your velocity is constant, and the speed of light has a maximum speed which it will always travel at. The second thing that must be understood is how a light clock functions. The clock depends on light bouncing between two mirrors to trigger the ticking of the clock. This is a key component to understanding relativity because it provides a great visual for time dilation and length contraction. Finally, the only equation that must be known to comprehend time dilation and length contraction is the equation of velocity, where velocity is equal to the distance divided by time. This means that velocity is proportional to distance but inversely proportional to time. With these three pieces of knowledge, it is possible to visualize Einstein's theory of relativity for yourself. Time dilation and length contraction are both phenomena which result from an object traveling at high speeds, especially when nearing light speed. Time dilation says that time will pass slower for the moving entity than the stationary entity. Another way to think of this is the faster you move through space, the slower you will move through time, where time will stop when traveling at the speed of light. And length contraction, which means that the observer will measure your length when moving to be shorter than it would when stationary. But why do these two things occur when traveling at high speeds? It is easy to see why this happens when we look at the path of light in their light clocks. To the stationary observer, the light in the stationary clock will bounce between the two mirrors in a perfectly straight line, whereas the light in the moving clock appears to follow a triangle-like path. This means that the light in the moving clock must travel a greater distance between each bounce in the same amount of time as the stationary clock, if time was constant in the universe. However, following Einstein's second postulate, the speed of light will always travel at 3.00 times 10 to the 8 millimeters per second. It is not possible for the light of the moving clock to travel a greater distance in the same amount of time as the stationary clock. Using the velocity formula, we can see that one of two things must change to keep the velocity of the light equal to 3.00 times 10 to the 8 meters per second. Either the amount of time between bounces must increase, or the distance between bounces must decrease in order to lower the fraction back to 3.00 times 10 to the 8 meters per second. These two changes directly correlate to time dilation, the slowing of time for a moving object, and length contraction, the shrinking of an object in motion. In reality, both time dilation and length contraction occur at the same time following Einstein's equations. If this seems like false information to you, you wouldn't have been alone, considering the number of physicists who also doubted the theory when it was first released. Today, several proofs for the theory of relativity have been published, which support time dilation and length contraction. The first proof, and the easiest to comprehend, was found by Joseph C. Hafele and Richard E. Keating when they put 3 cesium beam atomic clocks on different planes to fly around the world and kept the 4th clock at their laboratory. The clocks were first synchronized, then flown around the world twice, one plane eastward and the other westward. When they returned to the laboratory, the results were as expected, where the eastward plane lost roughly 59 nanoseconds and the westward plane gained roughly 273 seconds, proving time dilation is real. The second proof of relativity is found in muons, which are created in the upper atmosphere when cosmic rays collide with atomic nuclei. These muons are found to have a half-life of only 2.2 microseconds, yet travel at near the speed of light. Based on these numbers, they should only be able to travel about 600 meters, but since the muons are moving at near light speed, time slows down enough for them that they can travel all the way back to the surface of the Earth, which is about 100 kilometers away. The final proof of time dilation was discovered at the Hadron Collider. This is essentially a man-made replica of the proof by muons with other particles. The particles are accelerated in the collider up to 99.99% of the speed of light, and just like the muons, they are able to live well beyond their half-lives because time is moving slower for them. Unfortunately, there is no experimental evidence for length contraction yet, but Einstein's equation for time dilation is only true if length contraction also is true. With time dilation already proven to be true, we can accept the fact that length contraction must be as well. To recap, the three things that must be known to understand relativity are Einstein's postulates, the function of a light clock, and the equation for velocity. Time dilation and length contraction occur to keep the speed of light the same for all observers, which will slow time and shorten objects in motion. Finally, these concepts have been experimentally proven by atomic clocks, muons, and the Hadron Collider. Hopefully this video was informative and helped you understand special relativity, length contraction, and time dilation, and I would like to thank you for watching.